Hello everyone, and welcome to the 7th Lorna Casselton Memorial Lecture. As last year, this year's lecture is taking place online to continue the Memorial Lecture Series, which was established in 2014 in memory of Professor Lorna Casselton, an Honorary Fellow of St Cross College. Lorna was a renowned fungal geneticist and an enthusiastic promoter of science around the world in her role as the Foreign Secretary of the Royal Society. So being able to have a global audience online today is particularly fitting. The college is very proud to be able to hold this annual lecture to honour Lorna's memory. We're delighted to welcome Professor Ingrid Daubechies, who has been the first woman president of the International Mathematical Union to give this year's lecture on mathematics and art conservation. Ingrid is the James B. Duke Professor at Duke University, having previously become the first woman full professor of mathematics at Princeton University. She's been awarded a glittering array of awards and prizes over the years for her pioneering work on wavelets, including the Louis Unpound Prize, awarded once every 5 years to a Belgian scientist for work done before the age of 29. And in a career of many firsts, Ingrid was the first woman to receive the National Academy of Sciences Award in Mathematics, and also the William Benter Prize in Applied Mathematics from City University of Hong Kong. Most recently, she was named the North American Laureate of the 2019 L'Oréal UNESCO International Award for Women in Science, which is awarded annually to recognize 5 outstanding women in science and mathematics. And to top it all off, in 2012, King Albert II of Belgium conferred the very special honor of the title of Baroness on Ingrid. After Ingrid's lecture, there'll be time for questions, and these can be typed into the Zoom Q&A box. Ingrid, we're very much looking forward to your lecture. Thank you.
Since almost 10 years, I have been working apart from more mathematical pursuits, more scientific pursuits, I have been working on using mathematics to help art conservators. And that's what I want to tell you about tonight. So let me go to the lecture and show it to you here. I first have to share my screen. Here it is. And I'll go to presentation mode. Okay, so let me move this to the side. Mathematics and art conservation. Before I tell you about my own work, I want to tell you about a few other examples that have been done by other mathematicians and that might surprise you. So the first example I'm going to tell you about is work that was done by Massimo Fornaziere. He was then still a graduate student. He's now a professor of applied mathematics at the Munich Technical University. And then I'll tell you about how mathematical analysis helps with thread counts of paintings on canvas. And I'll talk about my own work and the work of my students on virtually aging and rejuvenating some paintings. Okay, the Eremitani Church in Padua, Italy, was famous for beautiful, beautiful frescoes by Mantegna and many other artists. After the Second World War, actually in the final days of the war in the Italian theater, it was bombed by mistake, and this was what remained of it. And all those frescoes had been reduced to rubble. I mean, here is a reconstruction of one part of the church, of the chapel where the Mantegna frescoes were. And here you see them projected back, digitally projected onto the top of the chapel. Actually, the bottom one had been preserved because it had been removed from the walls for conservation because it had water damage, as you can see. But the top ones were in much better condition and were all reduced to this kind of rubble, which was collected after the disaster and put in boxes. And every so often people would open the boxes and sigh and then close them up again. But in the early 90s, they realized that computers had made so much progress that maybe something could be done by something that's crowdsourcing avant la lettre in a certain sense. They stabilized and cleaned all the fragments and cataloged them. And they made a digital record of all these numbered fragments on CD-ROMs. Only the older ones among you will remember CD-ROMs, I'm sure. But in any case, there were a lot of data. And they asked people to come up with proposals to analyze these. So, and to find, not only analyze, but find where the pieces fit on the picture. They did have, as you saw earlier, these black and white pictures that had been taken with very high precision. Of course, there was some parallax because they were taken at an angle, but they could correct for that because they knew the exact measurements of how large the frescoes had been. So it was like having an enormous jigsaw puzzle of which you had some pieces, and you now had to puzzle them together, except that you had only a few of the pieces. I mean, the total painted lost area was over 10 times larger than for what they had fragments. And they had fragments that were really, really small. And not only didn't they know where, but you also didn't know what orientation. I mean, on many jigsaw puzzles, you can actually guess what the orientation is just from the way the thing is cut, but not here. So they needed a way to place all these fragments. Look how many they had, over 80,000 fragments. So, and Massimo Fornaciari came up with a very effective method that was the one used. So in order to explain the method, let me tell you a little bit about how you work with images digitally. So when you digitize images, what you do is you actually you cut them up in very, very tiny little squares, which we call pixels. And these pixels, if you think in grayscale, are then given a label from 0 to 255. 0 for all black, 255 for all white, if you work in 8 bits. And all the intermediate levels, these 254 numbers in between 1 and 254, are different levels of gray, from very dark to very light. So the you could say, well, then it's easy to recognize. You just look at the numbers and you see where the numbers fit. Well, it's not that easy, because if you move an image, like here I'm rotating an image, then the corresponding numbers would be completely different. So it's not so easy to see from two sets of numbers that they correspond to the same painting or to the same piece of painting. So Massimo came up with a way of trying to get the information that on the image in such a way that rotation is easy to deal with. So he used something that's called circular harmonics. And here I'm showing the images corresponding to some circular harmonics. So you see their ways of putting gray and white and black down in a very, very symmetric way. And what we know is that you can decompose anything you like in these circular harmonics. Any array of little square array or little round array of pixels, you can decompose in harmonics. And here's an example where, for the image that you see at the lower right, actually the decomposition is given. We have first a few circular, and then as we add more and more and more of these functions, which have these great symmetries, but not all the same symmetries, and that's how they can conspire to make something more complicated, you see that the image emerges. And any image can be, via a fast algorithm, decomposed in these circular harmonics. So, but they have the advantage that once you've decomposed your image in circular harmonics, so harmonic 1, harmonic 2, harmonic 3, and so on, with certain weights, what we call, the coefficients, then if you rotate the image, the harmonics, we know exactly what happens to them. In fact, they change by just a factor that depends on the angle by which you rotate them, and that we know that we know exactly. So the rotated version now will be decomposed in exactly the same way, except that the coefficients all acquire their own little rotated version, depending on which harmonic you looked at. So that means that if once you've decomposed the harmonics, you also have the harmonic decompositions of every rotated versions of the image. So in the Mantegna project, what was done was that the paintings had been digitized and stored digitally. And what happened is that, and for many different possible circles, all the different fragments on the painting had been decomposed in harmonics. And what volunteers would then do, sitting at workstations that were organized over the city of Padua, is call up from a fragment, then put in the biggest circle they could put in from the different radii that were allowed. And then they would say, so here's that circle. The machine would decompose in harmonics, check its whole database of that it got from the full painting, and give back an answer with the 3 top matches. And in over 80% of the cases, the top match was the right one. But it was in an overwhelming majority of the cases that the top match was among the first, that among the first 3 top matches was the right one. So the human volunteers usually had no problem deciding which of the 3 was the correct one. And that would then tell the conservators who had made prints of the pictures at a full scale exactly where to put it. And it always worked. And so the result of that is that they could put all these fragments back on the picture of the painting. And here you see for one of the paintings, it gives, you might wonder, what information does that give you? How does that help you? Well, look at here in this garland in the very top. We have a couple of fragments, but it has given you, it tells you about the color of these decorations and the background color in between, and some arcing here and a greenish color there. Let's look at a different one here. This tells you now enough to restore that whole frieze, because the frieze was clearly a repetition of the same. Here you have enough information at the foot of this soldier. You have enough information to reconstruct his sandal, the color of the inside of his shield, the color of his lance, the color of the tiles on the floor. So that little bit of information, together with the grayscale information which they already had, helps in restoring the images. And the conservators then use that indeed. Here's yet another one, which we'll revisit in a few minutes. Here is a version that, as you can see it in the church now. What they chose to do is for some swaths, just show where the fragments were, and for others, paint in a pastel color to clearly show, look, this is what we reconstructed and this is what the original is, what the painting, the fresco must have looked like. Here you see for other parts, they painted it more fully. Here you see when they were doing this reconstruction many years ago. Right now, it's open to visit for the public. But you could also, since we could do virtually all this reconstruction, maybe we can do virtual propagation of color. And yes, you can. So what you can do is you can, just like what the art conservators themselves did, take the information that you get and then propagate it out, said, oh, it must have been that red. And that means, and then, so you can do that by computing. And so here is an example of how that would be done from the fragments we have on the left. And the goal is, and that's something that Massimo is working on right now with students, that when you visit the exhibit, you would not only see the reconstruction, but you would also, with your smartphone, be able to see how it must have looked originally. That was one application. A second one, different nature. This is work done by Rick Johnson, who actually is the person who got me involved into using techniques I knew from image analysis and the mathematics accompanying that to art. So Rick Johnson is an electrical engineer at the University of Cornell. He's now retired. He always has been very interested in art, and he spent a sabbatical year in Europe in the 2010s, no, the aughts. And he got in touch with the conservators at the Van Gogh Museum, and he convinced them that maybe people who knew about image analysis could you show them useful tools for art conservation. And he then developed one himself. And I'm going to tell you about that now. So here you see a painting by Van Gogh. And art conservators like looking at these paintings with all the means they can. They are extraordinarily well-trained visual experts, but they look at them with X-rays, with infrared, and so on. And here you see an X-ray of the top corner of this painting. And I recognize immediately it's an X-ray because you see all the nails by means of which the canvas has been attached on the stretcher. It's also very clear that you see the threads, the weave of the canvas here. Now, that at first that seems a bit strange. How could you see the weave? I mean, X-rays go bang through textile threads. Why would they show up? Well, it's not really the weave that you see. Canvas, in order to not absorb too much paint, is not a raw canvas. It has been covered with a primer before painters paint on it, typically. And primer, until sometime in the 20th century, was something that contained a lot of lead white. And this primer, which is a layer that makes the canvas less absorbent, is applied on the canvas. And as you have this woven fabric with little valleys and little crests in between the threads, there is a slightly thicker layer where you are between threads than on top of a thread. And so you have this varying thickness of this lead white compound on top of your canvas, and that is very X-ray absorbent. So what you really see here in this picture is a structure of the lead white primer that was applied on top of the canvas. Anyway, you get what the canvas looked like on which the painting was painted. So when people, like they were doing in the Van Gogh Museum, write a complete catalog about artworks in their collection, they write things about all the conservation that has been done. They write things about the analysis of the pigments. They write all the documentation they have. And they typically talk about the canvas. They do a thread count in a number of different places on the canvas and say this was a canvas that was woven with this thread count, so many threads per inch. And when Rick Johnson heard this, he said, well, we know how to count how many things you have per inch. I mean, that's a frequency analysis. We have many tools to do that. And he developed a tool to do that automatically, together with a team of undergraduate students. So what they would do is they would take a tiny area in here, and they would then, in different directions, look at what kind of structure do I see that keeps repeating regularly. And they would find the angle under which it would repeat the fastest, which is the angle that's perpendicular to the threads, because if you have threads and you go perpendicular, then they repeat faster over shorter distances than if you go obliquely, when you have to march a little further to go to each thread. So, and so they made a display to count this regularity which you have and you see here already on this little patch, it's not exactly horizontal or vertical. It varies a lot. I mean, this is a painting on which you have a lot of the change of thread direction is very marked. You might say, well, didn't they stretch it properly on the stretcher? Well, you see the primer makes the fabric very stiff. It now has this compound on it, and you can't move it very much anymore. And if the fabric was a little bit not completely stretched horizontally and vertically when it was primed, and it never is because it kind of hangs on hooks in order to nicely dry, then those are now baked in and you cannot stretch them out anymore when you put the canvas on a stretcher prior to painting. Any case, so what he then did was that the information that he would have for the horizontal threads and the vertical threads, he would have two kinds of information. He would have information about how many threads do I really have per inch, and how much does the angle deviate from horizontal or vertical. So that gave him then 4 sets of information, but he could measure them all over. Well, it was done automatically by algorithms. He would get the X-ray and then they would take patches and compute it everywhere. And here you see one picture of density for the horizontal weave. And you see another picture of deviation from angle for the vertical weave. But he would have 4 such pictures instead of the 2 I'm showing you here. And all of a sudden, they could do things. The conservators said, look at that. We have a kind of fingerprint of the canvas. And they could do things like here. These are 2 canvases that have the same fingerprint in density of weave, deviation of uniform density of weave. These were still hand-woven canvases. So these paintings we now know were on pieces of canvas that Van Gogh cut in this order from the big roll that he would buy because it was cheaper by the dozen, I mean, cheaper by the big roll than to buy individual canvases. We know that because in one of those fingerprints, this is how they look. And you see how things line up. And in the other, this is how they look. And now this method has since been used on many, many paintings by many other artists. I mean, for instance, there's a painting by Velázquez that had been de-attributed. I mean, they said school of Velázquez, it's not really as good as the master. But then a canvas, this kind of canvas analysis showed that there's no doubt that it was a roll made. It came from the same canvas as 2 masterpieces, and it was nestled in between. And this was not canvas that the master was sharing with his students. So it was reattributed after this analysis. I mean, it was just the master on a slightly off day. Now, this brings me to what I want to talk about, which about my own work here. So I'm going to tell you about the GISI project and a fantastic adventure that I did with a team of graduate students and undergraduates who helped me in that task. But before I start on that, let me tell you on how this became part of my research interests. For those of you who know my work as an applied mathematician, I want to reassure you I haven't given up that. I mean, I do work on mathematics, mathematical results per se. I work on mathematics applied to biology and other scientific fields. But this is also, and it's a lot of fun to work on with students. Okay, so I started working on spurred on by Rick Johnson. And the very first project I was working on was trying to distinguish artists from each other or different periods in the life of one artist based on an analysis of image analysis. And what I used for this was a wavelet analysis. So let me tell you about wavelet analysis and what it does. It really determines information in the picture at different scales. So this is an image it's a grayscale image because I'm abstracting from color. We'll come back to color later, but an image of a pair of clogs painted by Van Gogh. And Van Gogh, because it was the workshop at the Van Gogh Museum that introduced me to thinking about these questions. And what you do in a wavelet analysis is, morally speaking, I mean, there's some more mathematical detail, but morally speaking, what you do is you compare the image and some blurred versions of it. Now, the blurred version doesn't look exactly the same anymore. So if you are going to look at the numbers in the digitization, it's not going to be the same numbers. And once you have numbers, you can look at a difference between them. And if I do that and then look at that difference as an image, well, I'm showing it you here and you probably don't see much here. I'm going to reinforce it. You see that you're getting edges because, of course, blur, where you have a swath of gray that doesn't vary much, you blur it, well, it doesn't make a difference. But where you have a sharp line and you blur it, all of a sudden things are different. So the difference of those two images is going to show up the edges. And you can do that, well, I'm going to show you doing this repeatedly, but I'm going to run out of real estate on my screen here. So let's look at a little piece. But you should imagine doing this over the whole painting. So this little piece I'm blurring, and again and again, and every time I can compute a difference. Now, in order to keep track of positive and negative parts of the differences, I'm going to give them colors. So I have several possible differences here. So these three differences, when I look at them, something stands out. First of all, the edge is something of the clog here, is something you see in all the images. Because, well, every time, if you have a sharp edge, every time you blur it, you lose something, and so the difference is going to show. But you have other areas. Here I have some detail that's kind of faint, that then shows up more and then starts disappearing again. So different details live at different scales. And so that's something that you can then use as information about the painting. And so we use that in our analysis by saying, if you have paintings, then we can look at the little patches. We can make a little statistic of every patch of there's so much more information that it reappears at this scale, at this angle, and so on. And we looked at different angles. So you make a little, what's called a feature vector per patch. Then you look at the whole cloud of feature vectors within a painting or in another painting, and that helps you see how different statistically are these paintings from each other. And we did that, and we then, and I'm going to go here to a movie. So we did that for all the paintings in a certain collection. And before I start the movie, let me tell you what I'm going to show you. In this, for all the paintings, we did that for all the patches, and we then computed how different are they. So they computed some kind of distance between paintings. And then we said, let's build virtually a mobile in which the distances at which they are in this three-dimensional mobile is about as close as possible to this collection of distances that we computed. And this is that mobile. And you see, well, the paintings with red dots are the paintings that in this collection were paintings that the Van Gogh Museum had told us had at some point be thought to be by Van Gogh. Some of them are in fact forgeries. So I'll point out one when it comes ahead. Other were paintings that had influenced him very much. Here's the forgery here, the one with the red dot that's at the front now. And others were paintings that were in his possession when he died, but that he in fact had swapped with another painting, Bernard, with whom he was friendly. And so it's striking that the red dots are more towards the outside of this cloud than the others. There are some paintings that are definitely Van Gogh and that are more to the outside as well. And in fact, although this struck people, and it's often quoted, I mean, oh my God, you can statistically analyze whether some painting is really by a particular painter or not. It's of all the work I've done on this in this topic, the one that is least appealing to me. But it led to more things, because what happened is that after I talked about this work, people would come with different questions. And so this was a challenge that we really enjoyed very, very much. This was a challenge that was given to me by Joris Dick. Joris Dick is both a material scientist and an art historian. And what they had studied, Joris Dick and Koen Janssen had studied a painting by Van Gogh that interested people a lot by a new method, by what was then a new method, by X-ray fluorescence. So this painting, the original painting, is a painting, a study of grass in bloom from Van Gogh's Paris period. And it was well known that underneath this patch of grass, if you put it on its side and you took its X-ray, you could see that there was something else underneath. It looked like a portrait of a peasant woman, and people were particularly interested in this particular portrait, even though there are zillions, well, not zillions, there are hundreds that Van Gogh painted in his Nuenen period, which was just prior to his joining Theo van Gogh, his brother, in Paris. And in this correspondence with Theo van Gogh, between Vincent and Theo, was preserved. And in this correspondence, he described that he was trying with a very, very dark palette with almost no light colors on it to nevertheless give an impression of color. And in one of the letters he sent to Theo in Paris, he said, and with this letter, I'm sending you a painting in which I feel that I succeeded particularly well. And so the letter is preserved, but the painting is not. People were interested in seeing this painting that Vincent van Gogh thought he was so well done from his Nuenen period. And well, of course, when Vincent van Gogh went to Paris, he changed his style completely. He met the Impressionists. Color became much more important to him. And it's not so improbable that this painting that he valued before, that would now become something that was just another canvas that he would cover again in primer to reuse. Actually, many painters do this with studies they've made, is reusing canvas, because canvas isn't cheap and Van Gogh was poor. So about 30% of his paintings, of his canvases, have something else underneath. So people were interested in this painting, and what Joris Dick and Koen Janssen proposed is to analyze it by X-ray fluorescence. In X-ray fluorescence, you send very, very high energy X-rays onto a tiny little patch of painting, and that ionizes some of the atoms there. And when the atoms then capture an electron again, in some cases, it drops back into two steps. They capture it in a high level step and then a low. And the energy difference in these two steps, in this two-step process, is characteristic of the atom at which you're looking. Different atoms have different distances like that. And so you can, by then looking at the energy, at the wavelength of the photons that come out, the fluorescing photons that come out, decide how much of particular substances, particular atoms, materials you have in different spots. And so they did that. And here are two wavelengths that correspond to arsine and to antimony. And you do see that there is a trace. I mean, this element was, the one on the left here corresponds to something, a component that was used in the vermilion that Van Gogh was using. And so you see the lips stand out. The antimony is a component of the Naples yellow that Van Gogh was using, which was probably the only light color on his palette. Remember, he was doing experiments with a very dark palette. And so it stands very much for the brightness. I mean, so it gives us a kind of black and white picture of the lady. And so with this and doing some colorization, Joris and Koen made this impression of the lady. We call her Lady 6 millimeters under. Many art historians don't like it so much when we call her that way. But, so this is the picture that you saw made the front page of a journal of analytic chemistry. But so Joris Dick told me, look, I mean, could we, as people who knew about images, with the data cube they had, so all these different wavelengths of different elements, do better. And so very generously, he shared the data with us. And the first thing we realized is that we had some weird artifacts. So you see here, I have an enlarged region. You have these kind of zigzag patterns. I said, what's that? I said, well, so in order to do the X-ray fluorescence, they needed a very high energy X-ray source. In the meantime, now that this method has been validated and used and so on, people have constructed special apparatuses that are used for the analysis of paintings. But at that time, those didn't exist. So in order to get that, they had to transport the painting for a hefty insurance fee to a teaching hospital that had a high energy X-ray beam from a synchrotron that was used to make short-lived radioactive components used for cancer analysis. And the way these machines work is that because they're very expensive machines and the beam of the X-ray beam is not used constantly for its medical purposes, is they make it in such a way that the beam can also be directed to a separate room where it can then be used for lab experiments, mostly by physicists who help pay for the machine. So Joris Dick and Koen Janssen had obtained some time to use this machine and for the analysis of painting. And so the X-ray beam came out. Now, the X-ray beam is not moved all over the painting. What happens is that it's in one spot and you move the painting to get a different spot examined by the X-ray beam. So they did that. And well, of course, sometimes this X-ray beam has to go back to its day job. So then you stop everything until you get the X-ray beam back, and then you start scanning again. And there had been a bug in that synchronization of when to move and when not to move. And since the picture was scanned in zigzag, that's why sometimes you had the black a little bit too early and sometimes a little bit too late. Well, what's the black? The black corresponds to an area where there was a lot of paint on the top painting, the one with the flowers, and so the X-rays couldn't penetrate. But all those should really have been one blob, not that zigzag structure. So the first thing we had to do is to correct for that. So every line probably had several breaks like that. And what we had to do is readjust mathematically, and we use mathematical algorithms to find the most likely spot of readjusting everything. After we did that, the black spots are spots where we don't have information because the X-rays couldn't penetrate and ionize and produce us this nice fluorescing picture. So, but I've told you about in painting, how we can propagate information. It's a painting. You have a brushstroke before and after the black. So you can see, you can infer what was hidden from you. So we made masks and we inpainted. And there were also places where there was long stretches in one direction because of the grass. We used a different method of inpainting there, and we got rid of those. Then we still had a problem with the eye. And we asked the conservators, and they said, oh, well, when when eye has been damaged, we use the other eye as inspiration in order to paint in that damage. And so we did that too. And then, so we had that picture, and you see here how detailed that painting in of these black spots on her face is. So then color. It turns out that with the elements for which we had information, we couldn't have all the colors. We were missing a whole lot of colors. However, we discovered that images that Van Gogh painted during this time, even if they looked very different, were in fact, if you analyze them the right way, color-wise, in some way not so different. So here are two images from that same Noonan period. One is one of the least contrasted one is one of the highest contrast ones. You see how yellow is the color that is the light color in both of them. And if you then look at where on the color wheel are you just make abstraction of everything that has to do with saturation or then well, they still don't look that different. But remember, black should not be counted, because black, whether it's very black purple, very dark purple, or very dark brown, or very dark anything, it always looks black. I mean, there's a zillion, for people who have an eye for color, there's a zillion different blacks. So if you remove the black, then in fact, they look not so different from each other. So what that meant was that we could use the information we did have and infer from other paintings what the missing colors, the colors we didn't have, probably were. We could interpolate here, and that would give us. So this is what the missing lady became. So our image analysis made us go from that left picture to the right picture, in which I hope you will agree with me that she came more alive. Okay, so this is how we use things. Let's come to the GISI project. Reunited. So this was the cover of a little catalog we made for an exhibition that was held in 2016 and 17 in Durham, in Raleigh at the Museum, North Carolina Museum of Art. So the North Carolina Museum of Art owned three panels of a 14th century altarpiece, of which they had their Italian art curator had discovered that he knew a fourth panel was in the Portland Museum, but he had discovered it was also the same as from the same altarpiece as three panels in the Metropolitan Museum and a central panel in the Art Institute in Chicago. The ninth panel that must have existed has been missing. So after they realized they all belong together, people looked into it and they couldn't find it. So he wanted to organize an exhibition where they would all be reunited, but the other museums weren't all that interested. They said, you have a missing panel anyway. And so enter Charlotte Kaspers, who is a fantastic artist in her own right. I mean, she is also trained as an art conservator, and she can, and she does, for museums, reconstruct paintings. I mean, she calls it reconstructing rather than copying, because she uses the same pigments and the same techniques as the artist originally did. So, and she has done this for a number of different museums, including for the Tate collection in United Kingdom. So they commissioned her to recreate that missing panel. Now, you can say a missing panel. It's one thing to recreate, as she's doing here, Jeroen Bos, so that it looks almost the same as the original, except that it's a modern painting. I mean, painted in the, that was still the 20th century then. It's another thing to do something for which you don't have the original. Well, we do and we don't. It turned out that it was very clear from the panels they had that it was followed the life of St. Evangelists, as described in The Golden Legend, a book that must have been a medieval bestseller, because there are many, many copies that we know of this manuscript. And so they could guess the topic of the missing scene, and then together with the art curator, they knew this was going to be the baptism of the heathen priest who challenged John in the Evangelists to see whether he would not be killed by the dregs of the poisonal cup that had been used to kill those two criminals. And when he drinks the dregs and doesn't die, eventually the priest asks to be baptized. And so that baptism was going to be in this missing scene. And what Charlotte did together with the curator was make a composition that surely is not going to be the same as the ninth one if they ever find it, but that introduced as few new elements as possible, so that it would not be their imagination. They used pieces of the composition of the other panels. Here you see her at work to make this beautiful new panel. and it was gorgeous. People were, I mean, the conservators were so thrilled to see her doing it with all these original techniques, and it became this bright jewel of a little painting in the style of Franciscuccio Gissi, and with the pigments that had been analyzed of this panel, of the other panels. So, and then they realized they had fantastic elements for their new exhibit. They had a documentary of its realization. They had this wonderful new panel, but there was no way they could put it next to the other ones, because this bright new jewel of a painting was going to attract all the attention compared to the older, but authentic ones, while the new one wasn't. So they, in that quandary, I said, well, mathematics can help. We used image analysis and image processing to age the panel. Since we had the same pigments in the new version and the old version, we could age back to what things should have been. I mean, we didn't try to age it. We didn't try to analyze the physics of it. I mean, that would have been a much bigger project. It was big enough as it was. They didn't want to age the object physically, because that would be a museum trying to produce something that could then later have been labeled a fake. I mean, that was not the goal. I mean, the goal was also to show this beautiful new thing. I mean, so how these paintings must have looked when they were new. So we did that, and we had to introduce cracks. So we needed to study the crack couleur. We had to find the color correspondence. We had to age the gold leaf work. And in fact, a printout of this virtually aged was used in the exhibit next to all the real panels. And it actually was less noticeable here in reality than on this photograph, where the difference in reflectance between the paper and of the print and of the panel, the varnished panels, exacerbated a difference that was not so obvious at the naked eye. But we could do more, of course, because once you can go in one direction, you can go in the other direction. You can take the old panels and detect their cracks. You can remap the old colors to new. You can rejuvenate the gold leaf work. And I knew we could do this because we'd done it before. So the craquelure is very dense. I mean, you might think it's easy. Well, no, it's not easy. Look at these cracks. First of all, there are cracks everywhere. Second, the picture of the crack here in the green coat looks very different from the dark in this orangey red curtain. Cracks don't look the same all over. You can't just take this color and change that. I mean, in-paint that. Well, you can in-paint. Nowadays, digital image processors do have in-paint techniques, but just detecting the cracks, we knew how to in-paint, I've shown you that, but just detecting the cracks was a problem. Well, we knew we had experience doing that because we'd done it with a very, very famous, much more famous than the Gissi altarpiece, with the Ghent altarpiece of Jan van Eyck. And in that altarpiece, which is a beautiful polyptych, newly restored, when you close it on the Annunciation scene behind the Virgin, there is a book. And people had been wondering whether Van Eyck had painted real letters, because, well, he was an incredible perfectionist, or whether he just painted little strokes to imitate letters. And when I was told this by art historian Maximilian Martens, I said, well, why can't you just try to read it? He says, well, we can't read it because of all the cracks. The cracks, it's very hard to see what the letter should be. We can't think the cracks away. Our vision system is, human vision is a fantastic tool. We do so many things. I mean, we can from three triangles, from a little figure, infer a whole lot. but we are very bad at thinking cracks away. So I said, well, we can do that. And so we did. It was much tougher than I thought. Actually became a big chapter in the thesis of a PhD thesis of an electrical engineering student in Brussels. But we did. And after we'd done that, I said, well, so we had in a portion of the Ghent altarpiece managed to fill in cracks. Historians had been then able to use this information and had been very excited because they felt recognizing some of the words helped them recognize those letters. So we had then used that that expertise in order to be able to fill in, to find the cracks in the Gissy paintings. Once we found the cracks, we could use our in-painting expertise to in-paint them. And here you see on the portion I saw you earlier, how I showed you earlier, cracks get in-painted. And here you can see how it's done very, very gradually. I mean, and actually we did it gradually because we wanted to stop at the stage where we felt we were going to infer too much. So we are inferring from brushstrokes and so on elsewhere, but you can do too much of a good thing. And so we stopped, and you still might have had some of the cracks. There's still some crack whispers of cracks available, but we stopped so that we wouldn't start removing information where it was not warranted. Okay, we also remapped colors. So here's an old panel, the 8th panel, and a new panel, the 9th panel. And you see how I told you that some of the elements of the composition had been borrowed from earlier from earlier panels. Here, the way St. John holds his mantle was borrowed in panel 9 from what you saw in panel 8. So to compare them, the gilding is something else. So let's take the gold away. Color remapping, after we've taken away the cracks. Here you see panel 8 with rejuvenated colors. Here you see panel 9 with aged colors. The aged colors, of course, would have to also not only be in the new panel, we had to age it, not only put in the old colors, but also introduce cracks. Actually, the crack density is very different in different pigments. And if you just saw a crack map, then you actually already see where the figures are, because the different pigments show cracks differently. So we had to take that into account as we introduce new cracks. Then in order to rejuvenate the old paintings, we had to also rejuvenate the gilding. That was more complex. The gilding, actually, it's very interesting because the painters in that Italian earlier Renaissance period, late medieval, early Renaissance, went to a lot of trouble to actually make a very smooth underface. I mean, they went through months of putting very, very even layers of gypsum under that had exactly the right elasticity to be able to be gilded. That's to say, they would put gold on it and then to burnish that gold so that you would have this polished gold in which you then with punch marks make very special effects for halos and such. Those halos, so Charlotte actually had punch marks made that we saw what the punch marks should have been from the other panels. She had punch marks made for this, and she did punch the new paintings. Okay, so in order to recreate the gilded effect on the old paintings, we actually had to find where all the punch marks were, and that was very tough. But we did actually, that was a method that was done mostly by hand. We identified where they more probably were and then adjusted. And then we had to model, because in order to get that gold reflection on there, you really need a 3D object. I mean, if you just take a photograph of something, something in metal, especially something flat. I mean, if it has relief, that's different. But if it's something flat, it just looks like a yellow thing. I mean, we actually perceive it as metal because we move our head slightly and the reflections change. So that had to be modeled. So we had our gold, and then computer graphics were then used to model and render the reflections on the gold background. Now I'm going to show you a resulting movie of that, of this rejuvenated object that exists only virtually. And but before I show it to you, let me tell you that you can find all the information about this GISI project and more on this website, Duke IPAI. IPAI stands for Image Processing for Art Investigation. It's our own version of CSI. Projects GISI. You have some other projects there too. But, so let me, without further ado, show the movie. So here you see this panel rejuvenated. So each of the panels from that were brought back, you see how we made it. I mean, the new colors are there, and you see how the punch marks change as we move virtually the painting and explore it over. So while this movie plays, let me tell you the conclusion of the whole project. So the exhibition was held. In the exhibition, people would see the reunited panel with the very the age reconstruction on a separate wall. They had the new one with all the illustration of the materials that were used. And there was a documentary of how it had been made. And then there was a fourth wall that showed on a big screen this animation, and that also showed the videos of the students explaining how they had worked on this and enjoyed working on it. And the exhibition, which they first had thought would be a very small one, having only very few very few people visiting it, very specialized, so on, became a big hit because people were so interested, and especially young people, in how all these computer techniques and this playing with images had given so much more new life to this painting. And that's where I want to stop. So I'm very happy to take questions, and I have been told that if I look at the Q&A, I can now see some questions. Okay, so a first question said the virtual propagation from the Montaigne project should be used by almost every restorer. Is it? And is the software available? So the software is certainly available on GitHub, which is a place where people post software that they make freely available to other software developers. The thing is that there's still a big step between software that people can use within image analysis backgrounds and an easy-to-use tool by people who don't work with image analysis. And that development has not been made. But as I said, some of it is something that Massimo now would like to do to make possible for with smart phones. So where you would scan in and so I don't know how far he is in that development, but there's a lot of really beautiful tools that are available. Actually, the painting that filling in missing information, which is used routinely now on smartphones, comes originally from the mathematical analysis that we also used for painting. It was developed by somebody called Guillermo Shapiro, and that's what's being used in Photoshop. Okay, so a question here is, don't frequent X-rays and other processes alter the original paintings? Well, first of all, they're not frequent. People take one X-ray, and usually in order to take a different X-ray, there are a lot of permissions that have to be obtained and so on. Second, when an X-ray is taken, it's just one exposure, and they have done experimentation to a great extent on pieces of every artwork, on little pieces near the edge that are under the frame and so on, to make sure that they're not injuring the artwork. But For the fluorescence, they had to make lots of little pictures, but every time it's only a very tiny little area. So the areas that's illuminated gets illuminated only once. So again, experiments had been done to make absolutely sure that they were not altering or damaging the painting. I mean, you can be rest assured that nobody is going to give you permission to submit a Van Gogh painting to something that would damage, if there were any risk of damaging it. Another question. Does this work require the development of new mathematics or new mathematical techniques? Or is it that techniques can be applied to very large volumes of data thanks to the power of the modern computers? Well, the second is certainly true. Some of this work could not be possible without the power of modern computers. Another thing, it is true also that techniques in a lot of what I've shown you had been developed earlier for different purposes that were then put to use here. But it's very interesting also that the questions that get asked by the art restorers in order to work to get results that are interesting for them are completely different questions from the standard ones. So I don't have the slides here, but we did some recent work on trying to separate X-rays. And in fact, I did work with that with researchers in England, with Miguel Rodriguez at University College in London, and people in image analysis group at Imperial. So when you have a painting on a panel, like in a polyptych of Van Gogh, of Van Eyck, that are painted on both sides of the same wood panel. You've seen art historians like, or art curators like to look, and art conservators at the state of the painting by looking at X-rays. If you X-ray something is painted on two sides, you get an X-ray of both things simultaneously. If you want to then disentangle those two things, because after all, you have the two visible ones, so you could say, well, this bit of X-ray comes from there and so on, but they overlap each other. Trying to unravel that, it turns out to be a very, very hard problem. And we've used traditional methods and developed new methods, and also had to look at new ways of looking at this question. And finally, it's some new machine learning techniques helped us get better results. But so the questions themselves, I mean, this is not a case where new mathematics has evolved, but I'm saying that because the questions are new, some of them may lead to us having to develop new mathematics. That's something that you never know ahead of time. I mean, but it may happen. And I expect it will happen. That's one of my motivations for doing interdisciplinary work. Okay. Somebody asked, what does this gilded effect refer to? Well, in these, it's my understanding, but it's very, I mean, you should really ask this from an art historian, that they wanted to show this beautiful, I mean, it wanted to attract the attention. I mean, these paintings were these old, in these churches, which were which were darkly lit with candles. And I can imagine that the candlelight on these gilded paintings must have made them seem very, very magical. I mean, we know that they went to a big trouble to burnish them so that they would, I mean, you can almost mirror yourself in that surface when it's just burnished. And then with the sponge marks, they would make a sparkle around the heads of saints. And okay. Talk a bit more about the methods you use for crack detection and generation. Okay, so these are the kinds of things that people often use machine learning for. Did you use that or more traditional image processing techniques? Well, when we did this work, machine learning is something that has burst to the foreground in the last few years, and machine learning was not at the stage yet when this could be done. Remember, the exhibit opened in 2016. we used, for the GISI project, we used only traditional methods. For, as I said, for X-ray separation, we're now using machine learning methods too. The crack generation, I have to admit that we cheated a bit, because we had a lot of cracks from the other panels, and so we could kind of lift cracks at the right density. The crack detection was hard, because you try to detect sharp features, of course, because the cracks are sharp, but the painting is full of sharp features, all the edges between different color planes and so on. So we used, in fact, we used 3 different image analysis techniques, and we said something was a crack only when at least 2 of the 3 techniques said it was one. And doing this kind of combination is something that's also done a lot in machine analysis. You use different ways of computing it, and then you do a pooling of results in order to get the best. Could these techniques be used to determine color restoration in faded or damaged textiles? Well, I think they can be used in lots of things that have changed color. But you see, we did not decide what the original color should be. We, in the GISI project, we had, for all those colors, we had an example of the new and the old. And so we could then make that shift. And it turned out actually that color mapping was easier than we expected, but partly also because of the painting technique. In that time, in this time in Italian painting, the painters, and Charlotte used the same technique in painting because she followed the manual of that time. They would make one color and then add a little bit of white or a little bit of dark in order to shade it, to get the gradations in the shading for the folds and so on. So what that means in pixel color space is that you have a very simple, if you take all the pixels corresponding to one piece of clothing, then they just form, it turns out they form a little plane in 3-dimensional color space. And you just have to shift that plane to a different location in color space in order to change the color to the right. We are now doing, there's a team of undergrad students that led by a very talented undergraduate who is in her senior year at Duke University, Ashley Wang, who is doing the same color rejuvenation on other paintings of the North Carolina Museum of Art, or also in the early Renaissance, late medieval collection, Italian collection. And there we don't have a version that has been repainted with the old pigments, with the same pigments as used in old times. So there we rely on the art conservators' detailed knowledge. I mean, we developed a little GUI on which the art conservator can say, yes, a little bit more, and so on. And they tell us the colors that are the right color, average color. And so then we can take those little planes and shift them to the right place. Okay. Somebody asks, is this technique also used to detect false paintings? I have no idea. But what happens is that it's not a question I'm very, very interested in, to be quite honest, because I don't have any standing in the question of deciding whether a painting is authentic or not. And I hope that the tools we develop will be a useful tool in the whole panoply of tools that art conservators and art curators will have. And if somebody wants to use them to detect whether a painting is a forgery or not, that's fine with me. But I'm not going to go into that because it's such a complete hornet's nest. And the last thing I want to do is to get in trouble with people who can provide these wonderful data to us and no longer have access because I'm now making dubious claims. So it's something I don't touch at all. So somebody asked, did they manage to rediscover the text in the Ghent altarpiece? And if so, what is it? So more needs to be done, but a first analysis seemed to indicate that this text could be a copy of the segment on the Annunciation in a book that had been written by a book that had been written, I forget which book it was, but there a book that a well-known medieval book that had a segment on the Annunciation, and that had been copied in Bruges a few decades earlier. So copies would have been available. But as I said, it still has to be investigated further. And that's all I know about it. And it's, as I said, Maximilian Martens, who is the art historian involved with the Ghent altarpiece restoration, is my source for this. And I should get an update on more recent update, but I haven't asked him recently. Okay. Okay, are there techniques available for looking at inks that are fugitive in water where the information appears to be lost? I have no idea about inks that are fugitive in water, but I know of very, very interesting work using image analysis and lots of beautiful mathematical approaches to recover information that seemed to be lost on what's called ostraca. This is work done by Barak Sober and his collaborators in Israel. So ostraca, it turns out that in old times, when people didn't have note paper available to write a little note to themselves, they actually sometimes used broken crockery. I mean, so if you have broken a pot, you had these shards of ceramics, which are extremely durable. You might write on that with some kind of paint and send a note. Yes, I got your message. I will be there at 5 o'clock tonight. Well, or whatever they would have said instead of 5 o'clock, and ask a kid to drop it off. And so those are ostraca. So they're often not very important messages, but they tell you a lot about everyday life. And what they found is that, I mean, these ostraca, because they were not meant to be messages for eternity. So when you find them centuries later, they're not very legible necessarily. So they worked on making them more legible. And then they found that in some places they could actually see with their methods things that were completely illegible or even not even suspected before. This was then very useful. I mean, not just for the content of the message, but because you can get a lot of sociological information. For instance, you could, if you can reconstruct them well enough, you can recognize handwriting. Then you can estimate in this small fort in the middle of the desert, how many people could write. I mean, and you can see that in some places, the number is so high that almost everybody must have been literate, while in other places it must have been just a select few. So there's really a lot that you can do once you can do these methods. But about fugitive inks, I don't know. But certainly you can use image analysis and information theory and so on in order to extract information when it seems almost lost. So some art conservators seem to like to restore paintings, and some like to keep its old aged looks. Now, you can show rejuvenations to its original. What can you tell me about your decision? I mean, it's very, very important. In what I showed you, I did not touch the painting. I mean, the painting is still its original thing. All I'm showing you is a virtual impression of what it may have looked like when it was new. What it can be used for is to help create virtual surroundings in which you can see how the objects in the museum were in everyday life. And I think that's really interesting. I think it's lovely to be able to see or to imagine these paintings with the candlelight reflecting on them. It's something that I didn't know about this burnishing of gold until I worked on these things. Now, when I go to a museum, whenever there are paintings of the spirits, I'm looking at the punch marks. But I think it's wonderful to be able to imagine more what life must have been like and how artists worked at exciting the imagination of people. But I never touch a single, I work with digital stuff and I make digital virtual things. I do believe that when those techniques are very more refined even than we have now, art conservators may influence their decisions about what to do, or the owner's decision about what they ask conservators to do. I think in some cases it stabilizing and the artwork and having a very good virtual recreation may then be preferred to trying to restore the artwork. But I mean, again, this is not something about which I'm competent or in which I would want to impose any or pronounce desirable points of view. I mean, because that's not, and also that's not what excites me about this. I mean, what I find exciting is helping people see what could have been. I don't have the dexterity to do the art restoration in the first place anyway.
Ingrid, I think we should probably acknowledge that we have worked you incredibly hard for a long period of time, and you've overcome some technical challenges. And just take a moment to thank you so much for the most wonderful evening. As Master of St. Cross, Mount Carasuta, I had the great pleasure of listening to world experts talking about things of all different kinds, many weeks of the year, and with Dr. Joe Ashbourne around to find fantastic speakers for our Lorna Casselton lectures. We're always learning something quite extraordinary. But some folk may know that my background is in heritage and grant giving in the heritage sector, and so I've been hanging on every word. I think that was a completely wonderful talk, and I'm struck by what an incredible joy it must be to work with you, Ingrid, because you've made such generous references throughout to the undergraduate and graduate students you've worked with, the colleagues you've worked with across the world, and you've obviously got a real passion for interdisciplinary work, which is something that at St. Cross we're really excited and engaged with right across the disciplines that our students and fellows are involved with. So I just thought it was so exciting to hear you talk in that way. And I also have to say that it's probably the first time I've heard a mathematician who was happy to use zillions as a unit of measurement. And I'm going to hang on to that thought for the future. Again, others will know that I'm not a mathematician by any means whatsoever, but your ability to share your work and to inspire with the enthusiasm and to give really honest answers. If you're not interested in whether something's fake or not, you're not going to pretend that you are. And I just think that's such a joyful thing to hear in a speaker of your stature and authority, to just be prepared to tell it like it is. So I think we've all had a fantastic evening. I'm so grateful for your time. And you've opened up all sorts of new worlds to me, and I'm desperate now to be able to get on a plane and come and look at some of these things that have been worked on with your sort of help and skills. And I think it just must be such a pleasure to work for you and with you. And all I can say is thank you so much. And thank you to the audience who've asked us some fantastic questions as well. And all the technical team who've managed to make it possible for us. So Ingrid, thank you. It's been an absolute joy.
Well, you're very welcome. Thank you so much. And I'm sorry for the technical problem we had.
It was not a problem at all. Thank you. And thank you, everyone.